So the question that I have up here might seem fairly innocent, and I haven't labeled this particularly as an example. The reason I say that is because this is a fairly important thing to note, particularly when you get to complex numbers, because this stuff will come in very handy. So again, we'll read the problem and we'll see where it kind of comes in handy. Let x equal to alpha and x equal to beta be the roots of some quadratic equation ax squared plus bx plus c equal to 0, where a is non-zero. By using identities, we want to show that if we sum the roots, it's the same as the negative b coefficient over the a coefficient, and the product of them is the constant divided by the a coefficient. Okay. We're going to have to use a little bit of stuff that's going to come possibly later. So if you haven't met the root factor theorem by this point, you are free to skip this video and just note that these results are going to be handy for later on. And when you have done the root factor theorem, what I am doing will make slightly more sense. So by using the root factor theorem, if we have the roots x equal to alpha and x equal to beta, then we get the factors x take away alpha and x take away beta both being equal to 0. Now, because we have two 1-degree polynomials and we're trying to get a degree 2 polynomial, this is where we can tune back in. If we multiply the two of these and expand, we're actually going to get a degree 2 polynomial. So what we're going to do is we're going to set the quantity x take away alpha times the quantity x take away beta as identically equal to ax squared plus bx plus c. Now we'll just expand things out as per normal. I'm not going to spend too long on expanding it because expanding by this point should hopefully be okay enough. So we get x squared minus, how will I do this? Minus beta x minus alpha x plus alpha beta is equal to ax squared plus bx plus c. So what do we do from here? Well, we're going to be taking a couple of comparisons. So one thing we can notice is immediately that a is going to have to be 1 in this case. However, when it comes to particularly the roots, we can transform this quadratic into whatever way we like. So we can actually treat the a as just a scaling factor and have it as a times x squared plus b over a times x plus c over a. And just completely ignore the a just for now. So if we compare just the x terms, what we get is negative beta x subtract alpha x is equal to the quantity b divided by a times x. So if we cancel the x terms because they're common to each of them, and then factor a negative sign out, where we get negative alpha plus beta is b divided by a, we can then move the minus sign over, and we get alpha plus beta is minus b divided by a, as required. So that was part A. Now for the x to the 0 terms, it's pretty much the same thing. On the left-hand side, we have the quantity alpha beta, the product of the two roots, and that's equal to c divided by a on the right-hand side, which is exactly what we want. So again, another QED can be inserted. Okay, so those two things you will be using for complex numbers when you're solving complex identities and complex equations, which we will get to in complex numbers. So that's going to be a story for us kind of at a later date. And note that this does actually generalize for higher order polynomials. Instead of adding and subtracting the roots, you're adding pairs and triplets, particularly if you have 4 powers. So just as kind of a little extension point, if we have alpha, beta, and gamma as roots of some ax cubed plus bx squared plus cx plus d equals to 0, then we can rewrite that The sum of the roots, alpha plus beta plus gamma, is going to be minus b divided by a. The sum of the pairs alpha beta plus alpha gamma plus beta gamma is c divided by a. And then alpha beta gamma is negative d divided by a. So it actually does generalize even to powers of 4. But of course, I'm not going to write that, and I will leave it to you, the viewer, to verify that this pattern roughly follows for higher order polynomials.